The so-called Lagrange points are those on which a light body can rest without its own power in a system of two mutually revolving bodies. According to previous opinions, the third body may only have a vanishingly small mass, while we now know that the speed of a driven body has in principle nothing to do with its mass. Therefore, under real physics, this restriction that the third body may only have a vanishingly small mass is released. However, the two main bodies must rotate sufficiently. Here, for the purpose of investigating the orbit of the Moon, we will mainly use the Moon as the third body to recalculate the Lagrange points. The 5 Lagrange points, L1 to L5, are drawn in the figure. The principle of the Lagrange points is that at each of these points the angular velocity of the Moon around the Sun is as great as that of the Earth around the latter, and it is constant. Because we already know how the Moon's speed came about, this problem can be easily solved. The Lagrange point L2 is a point located on the extended line between the Sun and the Earth. When the Moon is resting on L2, this means that the Moon's angular velocity around the Sun is equal to that of the Earth around the same. And the Moon's angular velocity around the Sun is a result of two forces, the Sun's and the Earth's gravitational field. It is calculated like this. The angular velocity of the Earth around the Sun is given by Because this formula holds, we have the following equation. If you solve this equation for RL2, you get this. This is slightly more than the 1.5 10 to the power of 9 meter calculated by Lagrange. On the same principle we have the following equation for L1. After solving them, we get the distance to L1. This is also slightly more than the 1.5 10 to the power of 9 meter calculated by Lagrange. Imagine there is a body exactly like that of the Earth, beyond the Sun at the same distance from it as the actual one. Then the second Earth is driven by the Sun to the same extent as the real Earth. Both Earths also drive each other to the same extent. Then the second Earth can rest there relative to the Sun and the real Earth. The Lagrange point L3 would then be exactly the point where the second Earth would be. If we take the Moon instead of the second Earth as the third body, the Moon, as well as the Sun, are further driven by Earth, but not reversal, because the Moon is considered here as a non-rotating body. This causes the Moon and Sun to revolve around the Earth. This effect is two orbits of the Earth and the Moon around the Sun from the point of view of the Sun. They are not equal and have an angular velocity difference delta omega. This difference could be in favor of the Earth or the Moon. Equilibrium is therefore only possible when this means that the Moon could deviate inwards or outwards from point B, the symmetrical point of the Earth beyond the Sun. Therefore, the L3 also has two options. From these considerations we have the following equation. Solving this equation for RL3 you get in two results. So L3 is 5.0610 to the power of 7 meter closer and farther than the Earth's symmetrical point beyond the Sun. When the Moon is on one of the Lagrange points L4 and L5, the Moon, Earth and Sun have formed an equilateral triangle and the distance between one and each other is r0, which is the distance between the Earth and the Sun. In these positions, the Moon and Earth revolve around the Sun in the same orbit and at the same speed. This fulfills the requirement for the Lagrange points that at each of these points the angular velocity of the third body around the Sun is as great as that of the Earth around the latter. This requirement is also met for every point that is on the same solar orbit as Earth. Therefore, a third body can only rest on these 2 points, because they are also on the same Earth orbit as the Sun. But why is a body stable on these 2 points? If for some reason the Moon has deviated somewhat from point L5, it will slip into zone 1, for example. Because the Moon's speed around the Sun there, inside the Sun's orbit, is faster than the Earth's around the same, it is accelerated into zone 2. In zone 2, because its velocity around the Earth is greater than that of the Sun around the Earth, it is propelled by the Earth's gravitational field into zone 3, which is outside the Sun's orbit and inside the Earth's orbit. In zone 3 its speed around the Sun is less than that of the Earth around it and so it will be moving backwards into zone 4. In zone 4 its speed around the Earth is less than that of the Sun around the latter and therefore it will enter zone 1 again. So he circles around L5 and approaches it more and more. It is therefore also possible to reach L5 or L4 in a natural way. At L5 the Moon is already so far away from the Earth that its gravitational braking effect on it has become so small that it can be neglected. Then the Moon is already able to rotate. In this way it also drives the Earth and Sun to move with its gravitational field. These then run around the Moon at the same speed. In this situation, a rotating Moon cannot disturb the balance of the whole system, it makes it even more stable. The principle for calculating the Lagrange points is the same as that for calculating the lunar orbit. We see that this three-body problem is solvable, although not that difficult. However, the prerequisite is that three bodies move on one plane and occupy sufficient rotational force. Therefore we can call it a three-body problem on one plane. And the previous three-body problem is unsolvable because, as I said, some basic knowledge is missing in previous physics. Thank you very much for your attention. See you next time.